So now we're going to begin our workshop. People might be coming along, but that's fine. We'll begin. This workshop will be recorded and be posted on our YouTube channel if you want to reference back. But today we've got our guest speaker, Deeya, who is a rising freshman at UC Berkeley studying engineering. And she's going to be teaching y'all and holding a workshop about quantum mechanics. So I'm going to hand over to Deeya, but thank you so much for coming here today and spending a bit of your time from your weekend to teaching us about quantum mechanics.
Of course, and thank you so much for that introduction and having me as a guest speaker here today. And hi, everyone, and welcome to Introduction to Quantum Mechanics. As a little intro to this workshop, I want to start off by saying that quantum mechanics is really a super interesting theory that governs the behavior of matter and energy at really the smallest scales. And in this workshop, we'll get to cover key concepts of quantum mechanics, a little bit about historical development, and actually also the basics of quantum computing, which you all have a chance to play around with at the end. So I hope you look forward to that. So I guess a little bit of a better title for this would probably be Quantum Mechanics and an Intro to Quantum Computing. So yeah, I hope that excites everyone. And if you have any questions at all, feel free to put it in the chat. I'll try to monitor it as much as I can and answer questions in live time or hold off some to the end. So yeah, feel free to ask any questions you have in the chat. All right. So I know people here may have different levels of understanding when it comes to quantum mechanics, so I wanted to take a little bit of a step back and really understand its roots and where it comes from. And to me, uncovering this history is kind of like the backstory of a superhero, which is a little bit unexpected, but super fascinating at the same time. Back in the late 1800s, classical physics was really what governed everything in the science world. It explained things like how apples fall and how planets move. But when scientists turned their attention to really the tiny worlds of atoms and particles, things became a lot more confusing. So in 1900, Max Planck became a very important figure, and he was grappling with a phenomenon that we know as black body radiation. And this is where things became um, a lot more interesting because classical physics couldn't really explain what was happening. So Planck actually took a step and he proposed that energy is actually doled out in tiny packets. So now you should picture energy kind of like a handful of gummy bears, not a continuous stream like most people expected. And this became one of the first quantum clues. If we fast forward to 1905, Albert Einstein jumps in. And he proposes that light isn't just a continuous wave, but a bunch of energy nuggets, which really builds on the ideas that Planck had before. This explained the photoelectric effect, which is where light kicks out electrons from a surface. So now light is doing both a wave and particle dance at the same time, which is what we know as wave-particle duality, which we'll explore more in just a second. Then the spotlight turns to Niels Bohr in 1913. And he was the one who really cracked the code of the atom. And he suggested that electrons have specific dance moves, I guess, around the nucleus, kind of like orbits. And this dance has different levels, kind of like floors in a building where energy is quantized in a sense. So there can only be specific levels of energy within an atom. In short, all of these bits of history show that quantum mechanics emerged because classical physics hit a wall when it comes to explaining the behavior of certain things. And while classical physics could really explain most of what was happening in the world, at the subatomic level, you have to use different tools, places where classical physics couldn't really explain. And quantum mechanics really did become that tool. And as we go through this workshop, I just want you to keep in mind that this history will really shape all of the things that we are about to explore. So one thing you may have definitely heard of when it comes to quantum mechanics is wave-particle duality. And for this, I want to show you a bit of a simulation that you will all have a chance to try. But before that, I kind of want to set the stage for what's happening here. So imagine we have a scenario where we have a beam of particles like electrons, photons, and a barrier with a single slit. Now, when these particles are directed towards a barrier, a screen on the other side captures its behavior. And in this case of a single slit, the particles pass through the open slit and create a pattern on the screen that corresponds to the shape of that single slit, which is very expected. And this is very similar to light passing through a single slit to create a diffraction pattern. But what happens when we have two slits? That's where things become a lot more interesting. So let me pull up this simulator and I'll put it in the chat for anyone else who would like to play around with it. Right. So this is what's known as Young's double slit experiment. Here we have a discharge tube, which is emitting a stream of particles at this screen, and there are two slits. And here is a screen in the back. And while you may have expected that if there are particles being shown, there should be the image of two slits on this back screen here, that's actually not what happens. Instead, we see this kind of diffraction pattern that shows up. And what's really interesting about this is it shows the nature of light as a wave. So if instead we were not emitting a stream of particles, but we were emitting two waves of water, we would see a similar diffraction pattern of waves interacting with each other. And the bright bold bands here represent where the waves overlap and their amplitudes add together. And black parts represent where their amplitudes essentially cancel each other out. So we have this diffraction pattern. And if you take a look here, you can play around with the slits width, wavelength, distance between the slits, and how far the screen is from the slits as well. What's really interesting is that if we switch over from this wave to particle view here, you can see if we emit single particles at this slit, you'll see the same diffraction pattern, even if it's one particle at a time. And this is very interesting because it shows that it's not just light as a wave, but light as a particle that also shows this diffraction pattern as well. And while all of this is super fascinating, there's even more to this experiment. Scientists essentially wanted to know what would happen if we observed which slit each particle went into. So they essentially put a sort of device next to the slits that could observe what slit each particle was going into. And what they found there was that as soon as they observed what particle each slit was going into, they saw the same two bands. They didn't see a diffraction pattern, but instead saw just two bands on the screen, which means as soon as they observed it, this diffraction pattern went away. And yes, there is a lot of math on this site if you go down, but this is basically explains what the diffraction pattern looks like based on the angle and stuff. I'm not going to get too much into the math for this workshop, but I think that basically essentially what happens from this experiment is so interesting because it shows that as soon as these particles are being observed, things change drastically. And that's something that's very important in quantum because observation, as we may think, is not something that's passive. When we observe something, it's an active process where light has to hit a certain particle for it to come back to our eye. Or in the case of observing in a different matter, we're still interacting when we observe. So when we try to observe what slit each particle is going into, essentially we're changing what's happening. And that's really important in quantum in general because observations will change the state of what's going on. And yes, this website is super cool. And if you would love to play around with it after this workshop, I highly encourage it. It's super interesting to play around with the different wavelengths, different slit lengths, and see how diffraction pattern changes. All right, let's go back to the slides. Okay, and here you can see essentially what's happening. While you originally might think that the particles just pass through the two slits and create two bands on the screen, the reality is a lot different than what we see. And this is really, really interesting because as the simulator showed, we're actually dealing with particles, not waves. And this is what really introduces us to a concept known as wave-particle duality, which is one of the basic concepts in quantum mechanics. It really shows that particles like electrons, photons, exhibit both particle and wave-like behaviors, depending on how they're observed or detected. This duality really changes what we think of with our classical intuition, and it shows us that the quantum world is very different than the classical world. Now, I know this slide may look super daunting, but don't worry. This is what we know as the Schrödinger equation. And this equation is basically like a maestro that conducts the quantum orchestra. It's what guides particles through this dance of uncertainty and probability. So imagine you're looking at the evolution of a particle's quantum state. This equation is really what tells you how that state changes over time. It's kind of like predicting the next move in a game of quantum chess. And this equation comes in two main flavors. We have the time dependent and time independent. The time independent version really describes how a quantum state evolves over time. It shows the particle's journey through various possibilities, and it's kind of like looking at a cosmic choose your own adventure story, really understanding what's happening to this particle over time. The time independent equation is all about more stable situations. It shows stationary states of particles where energy remains constant. And if you can imagine a particle in a box, that's basically what we're looking at for the second equation. And each one has a unique energy level. And what's really amazing about this equation is that it's not just this magical formula. It's actually rooted in mathematical elegance and physical intuition. And solving us gives us wave functions, which I'll dive into in just a second, which are basically all of the parts that particles play in this quantum orchestra. I don't want to get too heavy into the math behind this, but I thought it's really important to know and kind of understand a little bit better. And what's really interesting, and the reason why there are two equations, and the reason why we can have one equation that can explain both time variance and energy variance, is because of something known as the Heisenberg uncertainty principle. And that basically means, you may have heard this in the context of Schrödinger's cat, which I actually will talk about in just a second. But in fact, we can't know time and energy at the same time. And it's not just a matter of precision that we don't have enough tools to measure it. In fact, in quantum mechanics, it's physically impossible to know both of these at the same time, which I think is so interesting and fascinating, and something that really is pretty mind-boggling. And in terms of where did I learn all this stuff, I actually studied a lot of this on my own. In my free time. I think quantum mechanics is such an interesting concept. In my high school, I did have an introduction to modern physics class, which I took, which delved into the basics of this. And this summer, I took the IBM Qiskit program, which I learned more about quantum computing from. So it's really a lot of things that I've learned from different places all at once. But to me, quantum is such an interesting realm where basically your intuitions break down and everything you know is completely different. All right, and I know this slide also looks a little bit daunting, but do not worry. This is basically what we know as quantum states and wave functions. And basically, you should think of a quantum state kind of like a snapshot of a particle's mood. It's not about position, speed, or just any one thing, but rather like a combo package. And it's essentially a particle's way of saying, like, this is everything you should know about me. And how do we actually capture this multidimensional mood? That's actually where wave functions come in. And wave functions are kind of like the musical notes that compose a particle's song. They're mathematical functions that basically describe a particle's probability of being in different states. And one thing you'll hear over and over again in quantum mechanics is the word probability, because essentially we can't know any one thing for sure because of the Heisenberg uncertainty principle. We can't know multiple things for sure at the same time, which is why probabilities are so important. And basically, what's really important is that it's also the probability squared. And you can see here in the corner, it's all squared. And the amplitude squared of a wave function at a particular point basically gives us the probability density of finding a particle there. And the really interesting part actually is that the particle's actual location is uncertain until we measure it. And going back to the Heisenberg uncertainty principle, that tells us that certain pairs of properties like position and momentum can't be precisely measured at the same time. I find that so interesting that you really can't know both of those concepts at the same time. And for anyone wondering why it's squared, it's basically essentially to take the real values. But that dives a little bit into the math, which I don't want to get too deep into today. All right, so now it's time to go look at quantum operators and observables. And these are kind of like the detectives that reveal hidden truths about particles. You should think about these quantum operators as specialized tools. When you apply it to wave functions, they basically extract all of the valuable information that you could possibly want to know. The operator essentially interacts with the wave function and gives us things that we can measure. And each operator corresponds to a specific observable, something that we can measure or observe about a particle. For instance, this position operator allows us to find where a particle is, and the momentum operator tells us how it's moving. But here's the catch when it comes to quantum. When we're trying to measure an observable, the particle's state actually changes, and the act of measuring itself changes what we're trying to capture. And so this dance between measuring and altering is really at the core of this uncertainty principle. Oh, that's a good question. Sorry, I'll go back one slide here back to quantum states and wave functions. Someone asked in the chat, what's probability density versus probability? So the probability density basically essentially it refers to the probability of all things. So if we go back to the simulator, this might be interesting to take a look at quickly. If we go back to the simulator, and here I chose the particle view, you can see that as each particle hits this screen in the back, you can actually see where the bands start to go. And essentially, this is a probability density. The areas that are most dense on this image, like these three bands here in the front, have the higher probability of where a particle would go. So if there's a particle that's being pushed through these two slits, the density on the screen shows us which places have the highest probability. So the probability density essentially refers to areas that are more dense have a higher probability. I'm not sure if that completely answers your question, but let me know if that makes sense. Let me. Yes, it's not a value only between 0 and 1. That's what makes quantum so fascinating. I'll get into this a little bit more in just a second, but essentially quantum isn't something that's known as a superposition of states. So it's not just a question of 0 and 1, but it could be both at the same time. And that's what makes it so fascinating. Yeah, no problem. All right, so let's go back to the quantum operators. And like I mentioned before, when we measure this observable, the particle state changes. And the act of measuring actually changes what we're trying to see. And so that's what makes this realm so difficult because, like I mentioned before, observing is not a passive process. It's not something that we can just look at and then be able to tell. But the fact that observing itself actually changes the state, it makes it so tricky. All right, and so now getting back into the questions of zeros and ones, we'll get into this concept of superposition and entanglement. And these are two of the most baffling and mind-expanding phenomena in quantum mechanics. And they really challenge our traditional understanding of reality and offer a glimpse into the bizarre and really fascinating nature of the quantum world. So the first part of this is superposition, which I would call a dance of possibilities. In superposition, a quantum system can actually exist in a combination of multiple states simultaneously. And this really defies our classical understanding where an object is in one state or another, but never both. In the quantum realm, it can be in 0 and 1 at the same time. Has anyone here heard of Schrodinger's cat and that famous experiment? Yep, it looks like some people here have definitely heard it. It's a very famous thought experiment that involves a cat in a sealed box with a radioactive atom. And according to quantum mechanics, until you actually open the box, the cat exists in a superposition of both being alive and dead at the same time. And this highlights the peculiarities of the quantum states. Because until you actually open that box, until you observe what is happening inside, the particle, or in this case, the cat, remains in a superposition of states. It's so interesting to me that observation changes everything in this quantum realm. And that actually leads to the next part, which is entanglement. And this is what Einstein famously called spooky action at a distance. Entanglement is this super perplexing phenomenon. And the way that you should think about it is that these two particles become intertwined in such a way that a state of one particle influences the state of another, regardless of how far apart they are in distance. And this instantaneous connection is so mind-boggling because it seems to violate the limits of the speed of light. As many of you may know, it has been assumed that nothing can go faster than the speed of light, and that includes things like information. Yeah, it does violate it. That's why it's so interesting. Nothing can go past the speed of light, including information. But what entanglement tells us is that this connection between two particles is instantaneous, regardless of how far apart they are, which means that the state of one will affect the state of other instantaneously faster than the speed of light, which we assume should not happen, but it does. And entangled systems are very much real. And the reason why this has such broad implications is because this can actually affect things like quantum computing. In the quantum world, particles can exist in superpositions of various properties like spin, position, etc. And this phenomenon becomes really fascinating when you extend it to larger systems. And this is how quantum computers operate, because they exploit things like superposition to do really powerful calculations. And quantum computing, bits or qubits can exist in superpositions of zeros and one, which enables things like parallel processing, and this can help solve problems that are infeasible for classical computers. So let's talk about quantum computing, and this is some of my favorite parts because this really shows the applications of these concepts and the ways that they can make a real impact on the world. So to start off, let's talk about what qubits are. And qubits are short for quantum bits, and they're basically the basic unit of information in quantum computing. And it's the counterpart of a bit in classical computing. And a qubit plays a very similar role as a bit in the sense that it stores information, but it behaves a lot differently because of the quantum properties on which it's based, which are superposition and entanglement. And here you can see kind of some of the differences between the two. In classical computing, information stored in bits versus qubits. And because quantum computing has qubits that can exist in multiple states at once, the possibilities for computation are endless. And this is why people are so interested in quantum computing. It's essentially because that they're able to do so many more things than our classical computers can because of its processing power and the fact that its qubits can exist in multiple states at once. And to show this, take a look at this. A quantum computer can do so much more with its qubits than a classical computer can with the same number of bits. So if you think of a 2-bit register, a classical computer can only store one of 4 binary configurations, which are 00, 01, 10, 11 at any given time. And someone asked, what is a state? So a state is essentially what an object can represent. So in terms of classical, that could be in a 2-bit register, a state could be 00, 01, 10, or 11. In the sense of a 2-qubit register in a quantum computer, it can store all 4 numbers simultaneously. And as more qubits are added, the number of states actually increases exponentially, which I feel is so fascinating because if you take a look at it here, if you have 2 bits and 2 qubits, you can store the same amount of states, which is 4. But as you go up to 100, you can see the vast difference in the number of states of a classical computer versus a quantum computer. In a sense, a state is basically what it's able to represent. And in a classical computer, it can represent a very limited number of states compared to a quantum computer. All right. In quantum computing, and specifically the circuit model of computation, they're what we know as quantum logic gates, or they're also known as quantum gates. And these basically operate on quantum circuits with small number of qubits. And these are basically the building blocks like classical logic gates are for digital circuits. And you can see here, there are some examples. They're the Pauli XYZ, and you can see the matrices that are applied to it. So these are what the gates look like and the specific matrices that they apply to. And these basically control the spin in the XYZ directions. We have Hadamard gates, which essentially change it into a superposition of states, different phase gates, C0 gates, swap gates, Toffoli gates. I won't get too much into these because I know that they can be a little bit complicated to understand, but essentially what happens with each of these gates is that it applies a matrix to the different qubits and changes its state essentially. And now I think it would be really fun if we did a little bit of quantum computing for ourselves. Someone asked, do they share the same function as logic gates like OR, NOR, and stuff? Yes, they're very similar. So if I go back, we have C0 gates, which are essentially one of the NOR type of gates. It applies a knot to the second qubit. A CC knot, also known as a Toffoli gate, applies it to the third qubit. There are differences between quantum and your classical circuits, but there are similar operators between the two of them. So they can do similar things, but the processing powers are vastly different. And in order to explore this a little bit, I think it would be fun to try to do one for ourselves. So I will put this link in the chat. You may need to create an account with IBM Quantum, but I will share my screen for those of you who are not able to. We can look at one together.
I'll also put it in the Discord chat.
Yeah, sure. Someone asked in the chat, does Pauli have anything to do with Wolfgang Pauli? Yes. Actually, the gates are named after the physicist Wolfgang Pauli, and these include the XYZ gates. And basically, the X gate flips a state of a qubit from 0 to 1 or from 1 to 0. And the Y gate is in the imaginary. And yes, they basically are named after that physicist. It's a great question. All right, let me share my screen. And if you are able to log in, there is something called the IBM Quantum Composer, and that is what we're going to look at today. So if you click on that, it should take you to something that looks like this. And here I have a very classic Bell state, and I'll explain what this does. And I feel this composer is actually so useful when it comes to playing around with quantum because it shows you things visually. So here we have two quantum qubits here. This is our 0 qubit and our 1 qubit, and C2 represent our classical bits. So C2 represents the 2-bit register. And here we have a classic Bell circuit, which is a very basic circuit in quantum mechanics. And essentially what it does is there's a Hadamard gate applied to the 0 qubit. And then this is what we know as a C0 gate. It applies a naught to the second qubit. And what both of these gates here do is measure it from a quantum state to a classical state. And like we mentioned before, observation is not a passive process. It's something that's very active. And by observing something, you are essentially changing the quantum state. So when we observe it and measure it into a classical state, we're essentially forcing the qubit to no longer be in a superposition of states, but rather choose a specific state that could be measured. Here at the bottom, you can look at the different computational base states and the probability of that happening. So here it took 1,024 shots. And essentially what it means is it ran this circuit 1,024 times. And in that, there was a 50%, essentially 50% probability of this basis states being 0, 0, and a 50% chance of it being 1, 1. And this Q sphere here shows what's essentially happening to this quantum bit. And you can see the state as well as the phase angle. So let's say I delete these. Now you can see what this Hadamard gate is doing. And it's very fun to play around with it visually and see what's happening. And over here on the right, you can actually see what the code looks like. So here, this is a very interactive drag and drop aspect of quantum computing. But if you know Python, you can learn Qiskit, which is essentially how quantum computers are coded and how we actually interact with them. And here you can see what that code would look like. So QReg essentially refers to your quantum register. And here we're saying we want a 2-qubit register. And CReg represents your classical register. And here we have 2. H represents a Hadamard gate, and we're saying that we're applying this to the 0 bit. Now, if I go back, here we set this is our C0 gate, and we're saying we're applying it to the 0 qubit and the 1 qubit, and then we're measuring the 0 qubit into the first classical bit and the second qubit to the second classical bit. And on the side, you can see so many different operations. And there's so many. and each one does different things. They apply different matrices to your qubit. And so I definitely suggest, if you're interested, to play around with these, see what they do. And if you want to look at it this way, you can take a look at what the names of these different gates are. So these are your classical gates, and essentially the classical gates apply a classical operator onto a quantum bit. So the not C naught gates swap identity. We have different phase gates here, which essentially change the phase of the qubit, and as well as other gates. So yeah, here is a very basic bell circuit and what its code looks like. Right. Go back to the slides. And we played around with the quantum computing aspect of this, but there's so many more applications for where quantum can go in the future. So like I mentioned, there's quantum computing, and these are really the stepping stones to the future. Quantum computers use qubits to perform really complex calculations at lightning speed. And that's because its processing power is so large compared to classical computers. So if you thought that your computer right now is running super fast, just imagine what a quantum computer could do. We also have quantum cryptography. And so quantum cryptography really is so important because it uses the properties of quantum particles to create really unbreakable codes. It's kind of like a conversation in a language that only you and your friend understand, and you can't crack the code without leaving fingerprints all over it. And this is because of entanglement. And if we use entangled particles as the lock and key, only someone who has one of those particles could actually figure out what the message is. And so this has really huge implications for cryptography. There are also quantum sensors. They can detect the tiniest vibrations or magnetic fields, and they use the sensitivity of quantum states to measure basically what's immeasurable right now. Whether it's mapping brain activity, searching for underground minerals, these really redefine what we can sense and what we can measure. And then finally, we also have quantum materials. And quantum mechanics really doesn't just affect particles, it can also transform materials because these have unique properties that defy classical expectations. The potential implications of these are creating innovations like superconductors that carry electricity with zero resistance, or new materials with extraordinary strength and conductivity. And so as I'm wrapping up this workshop today, I just want you to take a moment to reflect on how these really bizarre concepts are revolutionizing technology and really redefining what's possible. Quantum mechanics isn't just a theory, it's really a catalyst for the next generation of innovations. And thank you so much for attending the workshop today. If you would like to connect with me on LinkedIn, send me an email about any questions you have, please feel free to. And if anyone has any questions that they would like to ask, now's the time. Yeah, thank you so much to everyone who attended, and I really hope you learned something new. Yeah, thank you so much, everyone. And if no one has any questions, I would highly recommend playing around with the simulator, and especially IBM Quantum. If you know Python, if you're interested in it, you can definitely get started on learning quantum computing and just playing around with it and having fun. What do I do with this knowledge? Do I compete or write? That's a great question. So like I mentioned earlier, I am actually just starting college. I will be a freshman at UC Berkeley in the fall. and my major is engineering physics. And I'm very interested in quantum, so I hope in the future to get involved in quantum computing. And with this knowledge, I'm really interested in working on code for quantum computers. And I really think that this is the next big thing and can be have really big implications. Someone asked, could you go over the table, the difference between quantum computing and computing? Yes, of course. Let me go back to this table right here. All right. So going back to this table, I think some of the differences between them is in classical computing, it's more limited in the sense you're using bits, which can only be in 0 or 1. In quantum computing, on the other hand, you can be in a superposition of states, which means you can be in 0 and 1 at the same time, which means that instead of having a discrete number of possible states, there's an infinite continuous number of possible states. This also means that whatever you're inputting into a quantum computer can have multiple outputs to the same input. So if I put something in, basically different answers at the same time. The logic of quantum computers are a little bit different than classical computers, as you saw with the different gates. They're determined more by linear algebra and matrices rather than Boolean algebra. And it's obviously very defined by quantum mechanics rather than classical physics. So I'll leave this up here if you're interested, and you can take a look at it. Let me know if you have any specific questions related to this. Awesome. Well, thank you again, everyone, for attending. I really hope you learned something from this. And like I mentioned again, feel free to email me with any questions you have in the future.
Thank you for hosting, Deeya. It was a wonderful workshop, and I see many people enjoyed it in the chat. And yeah, we'll keep it a wrap. If you'll have any questions, you can stay on Zoom or contact. But we will wrap it, just leave the meeting in a couple of minutes. So yeah. Okay, yeah, I think we're done. But thank you so much. It was genuinely a wonderful workshop.
Thank you so much. And thank you for having me.
Yeah, of course. Okay, have a nice day.